Today. 15A, chapter 15, we're moving on to continuous random distribution. What did you learn yesterday? Can I please have, let's go with Aiden, what do you remember? Good, integrating with infinity sign. So we had negative infinity to infinity. What am I integrating? Can I please have Phoenix? A continuous what? You're right, it is continuous. It is not probability, it is what, Naz? It is a probability distribution graph, but it is not a probability distribution. It is what distribution? It is what? We're not integrating by probability and x-axis. It's not PR of x. It's not P of x by x. What is it by x right now? What is it? And that makes sense as to why we integrate this as well. What is this thing that we're trying to integrate? It's not probability, because if it's probability, it would mean that when x is 1, whatever this value is, let's say that was 0.7, then this represents probability, that coordinate, but it doesn't. F of x. We find the integration of f of x dx, but then what is f of x? What is f of x describing? Why do we integrate? Okay, so we've got to start questioning all that. So why do we integrate? And then why, or what is f of x? Those are the two questions I want you to think about. So I just said it's not probability distribution because it's not probability by x-axis. Okay, the x-axis is your continuous variable. This is continuous, that's true. But what is f of x? So we're now calling this your y-axis, and apparently whatever this is your f of x. We're integrating means we're finding the area. Anyone remember why we're finding the area again? Why are we finding an area? So why are we integrating? Just find if it's 1 or not. It's true, but what is 1? Why do we want 1? Because it's probability. So it's not the graph that represents probability. What is representing the probability? The area. That's why integration, we're now saying it is the area. Why is the area the probability? What was my logic from yesterday? So why is the area now the probability? Why is area equal to probability? What's the reasoning? Why are we doing that? What's the area equal to probability? Yes, Naz. Got the right idea, but it's not why we do it. It's not why we do it. It's not why we do it. You are right. We were trying to get as close to a particular value. We can't get a particular value, so we get an interval. Now remember yesterday I said continuous, the difference between continuous and discrete. Discrete you can count. So if you can count, that means if I ask you to find the probability at exactly 1, you can tell me. So it's kind of like, think of a string, that's length. Length is continuous. If I ask you, what's the chance of you randomly cut exactly at 1 centimeter? Well, it's 1 out of what? We don't know the possibilities. So that's why we can't do 1. But what could we do? We could find the probability if we did the... What did I do yesterday with 0 and 6? The string. How did I get you guys to give me a probability? We couldn't find an exact point. What did I do? How did I change the problem? An interval. So an interval, which is going back to what Naz was saying, that we're closing it onto, I might not be able to find a point, but I can find an interval. So whatever the point is, if it was exactly 1, then maybe I can do 0.9 and 1.1. I can do an interval between those two, and I'll get very close to getting 1. Okay? So with continuous, I can't do one specific point, but I can do over an interval. Because it's an interval, that's why I said, okay, so that means if I can model a problem with a function, okay, which is why I call it f of x, model a problem, meaning that if I wanted to predict whether you are going to succeed in year 12 or not, x by doing the hours that you study, and this is the success rate, okay, this is a model, I just made it up. Somehow I figured out this is the equation, this is the graph for your success, right? So if you study about, I don't know, 10 hours, then there's a dip. If you study more than 10 hours, it goes up. If you study just less than 10 hours, it goes up here. Okay? I don't know that, right? But let's say I made it up. This represents, this models our situation. That if I want to find the chances, I want to know the chances if you study between 1 and 10 hours, what's the chances of you succeeding? Yeah? Then, I know that for continuous, it was best to find out the probability by doing interval. That's why we integrate. But the problem with integrating, or finding an interval, is that every time you integrate a function, it doesn't mean it can model our problem. Why? Because probability has a few things that it can't have, which is what Aidan was saying before. He said that the sum of all probabilities, if you integrate it, it has to equal to 1. Why did it have to equal to 1? Because we said the area now represents probability. But if it's probability, you can only have 100%. You either get it all or you don't get anything. That's why I have to equal to 1. The other thing we also know, if it's probability, it also can't be negative. Those are the two conditions we learned yesterday. And we call this function, if it all fits the conditions, we can model our situation with this f of x, and the area is now the probability. We call this the, what's the name for this? Good, probability density function. Okay, are we starting to sort of see the picture of what's going on? So if I were to break this out, this is not a probability distribution function. Okay, because distribution means that I'm doing x variables by probability y-axis. That's what we did for discrete, because we were able to count 1, 2, 3. How many times did we get 1? How many times did we get 2? And I could find out the chances. And that's why it was a probability distribution. This is not a probability distribution because I couldn't do it for just 1 or for 2 or for 3, because continuous I couldn't count. So if this is continuous, what they figured out is, well, what if I were hypothetically able to model? Your job is not to model. They give you the equation. They give you the function. Okay. If it was able to model a situation, then what can we say about the area? We know that continuous we can do intervals. Intervals can be the area. And so that was the hypothetical. That was what we made up. We just said, wait, what if we found the interval, which means the area, the space between it, if the whole entire thing was 1 and I got half of it, well, that's 50% chance. That's why we know, all right, let's do the interval instead. So if the interval represents probability, then how do I know that this model will work? There were two conditions that had to work. All of it, the area has to equal 1, because the area now represents probability. 2, the area has to be above the x-axis because probability has to be positive. Those were the two conditions, and then we gave it a name. We said it's probability density function. But does that make sense as to why it's integration negative infinity to infinity of f of x? Because f of x is a model. I don't know what the model is. It could be anything. That's why when you're doing the examples in the textbook, it could be crazy. It could be anything. It could be quadratic, it could be linear. I don't know what it is. And apparently it models our situation. So it could be anything. It could be the chances of me trying to study the chances of your weight gain over year 12. What? The number of hours studying how much weight gain you've gained, okay, over the course. So how many of you gained 3 kilos, 2 kilos, 2.1 kilos, okay? I'm measuring it over a distribution where x is the weight, and let's say this was the model. Somehow I figured it out. Somehow I sat down and made up some equation and it models it. It fits your data, okay? So you might have 2.1 people, 2 people are at 1.1 kilo gain, 3 people are at, I don't know, 7.2 kilo gain, and I've got this prediction. For 25 kids in my class, I'm able to predict using this formula, right? I call it f of x. Then, if I want to use this model to predict, then I have to make sure this model works in terms of probability for you guys. And that requires two conditions that it needs to satisfy for it to work. Does that make sense? So I can make up any function, but the function doesn't mean that it can be used for probability. That's why as soon as they tell you that it's a probability density function, you know. It all adds up to 1. It's above the x-axis. That's what you know. Yeah? Okay, so that was 15a. Cool. Now, that was the hardest concept really. If you've got your head around what I was trying to say just now, 15a, that was the hardest part. The next parts are all easy. Everything else, remember, like binomial, the hardest part was understanding what binomial is, Bernoulli sequence. After you know that, expected variance. Memorize the rules. It's the same thing now for continuous. Okay, so when I move on to the next page, so you can see, if I move on to expected value and variance now for continuous. So we want to know the mean, we want to know the spread, and we want to know the standard error, or standard deviation. So, same idea, expected value, we already know from chapter 13, this is your theory. Expected value is sum of your x variable times the chances of that variable occurring. We already know that. Now, how do you convert that to continuous? Now, x is the variable, so we can still have x multiplied 2. Now, to find probability, how do you find probability again? It was the integration. So it's really just x times the integration, or the function, area of the function. That should give you, if you integrate all that, that should give you the expected value. Yeah? So instead of doing it like this, instead of doing this, integrate from negative to area of f of x dx, that will give you the probability. True? But you just said take probability times x. So here we go. Voila. Suddenly, you got yourself a formula for expected value. So if I show you the next step, so look at that. How's that different from what you already know? It looks different, but theoretically it's the same. So theoretically, you knew negative infinity to infinity of f of x was the probability. What did you say here? We said times by x. That's what I'm doing. X times the function. Okay, function, and find the area of that. That's my probability. X times the probability. Sum them, because remember integration means sum. All those probabilities together, where you times x to it, it's exactly the same thing as saying this. You're saying sum all the x times probability. I'm doing the same thing. I'm doing x times sum all x times f of x times f of x for every probability. Sum them all together. So this is continuous. But you see the continuous formula for expected value comes from chapter 13. What you've learned, theoretically. Okay? So that's what I mean that when you're doing your exams at the end of the year, your job, what was the hardest part? It's not doing all this memory stuff you can memorize easily. It's on your formula sheets as well. The hardest part is determining what x represents. What is the problem? Because if you know it's continuous, you've got this. If you know it's normal, you've got the next chapter. If you know it's binomial, you've got the previous chapter. You know it's chapter 13, there's conditional, addition rule, mutually exclusive, independent, condition. Yeah. Actually, I said that already. Okay, so hardest part when you're doing probability is determining what is the problem. Okay, it's not doing these formulas. So for 13b, this is your expected formula. That's how you find the expected value, and then variance is going to be exactly the same. Actually, I'll go back to that slide. Where's variance? Did I put variance? I thought I put variance. Oh, yeah, I did. Here we go. Variance, same thing. We said theoretically, we said that it's the mean or the average of your x data, so what you guys got, minus from what I predict you to get, so we can find the error, but then because you can have a positive error, negative error, we square it to eliminate that problem, right? Then technically, you already know E of x. So if you know how to do E of x for continuous, then you know how to do E of x minus mu squared for continuous. All I'm replacing is, instead of x times f of x, what am I replacing? The x to be x minus mu all squared. See what I'm doing? So even if I asked you right now, how do you do for continuous to do E of x squared, it should just be the same as what you were doing before, integration for f of x dx, but the only difference is instead of timesing it by x, you would times it by, say it again, x squared. That's what it means. E of x, the expected value you told me was integration x times f of x. Right, that's what we just wrote down. Then when it comes to variance, which is over here, variance was E of x minus mu all squared. Then it's the same thing, negative infinity to infinity of x minus mu all squared times f of x. This is nothing tricky. It's exactly the same things. So my students, every year that I teach, the confusion to I keep getting the same students asking the same questions. They will know how to do E of x, but they don't know how to do E of x squared, which is strange to me because it means exactly the same things. If you know how to do chapter 13 E of x squared to find the variance, then it's the same thing for continuous. There's no difference. The theory is still the same. E of x was x times probability. Then E of x squared means x squared times probability. And then same thing with E of x minus mu squared. It's the same thing as x minus mu squared times probability. Same theory. Okay? Nothing different. So that means if this is the theoretical formula for variance in continuous, then does anyone remember from chapter 13, what was the formula for the computational one? Because I gave you two formulas for variance. I said one was easy to do with a calculator, and one's good for theory. What's the formula again for variance if I want to do the computational one? What was it again? What's the computational formula for variance? The one that could be much easier to solve. Anyone remember? Yes, Daniel. E of x squared, yes? Very good. This is your computation formula. If you forgot, go back to your notes, but it's going to be the same one for every chapter. 13, 14, 15, 16, 17. You're doing the same things. Okay, so if you've forgotten it, write that somewhere that you know you're going to be using. This is the easier formula than doing the one I just showed above. Okay, and we know how to do this one now. This one is just integration negative infinity to infinity of x squared times f of x dx minus, well, you know how to find e of x. It was integration negative infinity to infinity of f of x times x dx all squared. That will give you the variance. And that's exercise 15B. And that's why I'm saying that probability, you can really whip through it because the theory comes from chapter 13. Formulas for each chapter is different, but they all come through the same idea. Okay, so 15B, you're just going to be practicing doing your integration. So this goes back to chapter 11. If you couldn't integrate well, this is where it's going to catch you. Okay, if you can't do definite integrals, that's where it's going to catch you. Okay, but the theory, it's not hard. Probability as itself is not hard. But 3/4 of the course, as I said, was calculus, functions, and algebra. This technically, I've taught you the theory, and I know that most of you know the theory. It's the question of, can you now do that? So if I gave you a problem from chapter 15, 15B, could you integrate? Because that now goes back to chapter 11. It's not chapter 15, it's a prerequisite skill. That's why if you can nail down the first three pillars, probability is very easy. It's easy to pick up. Okay? Do we have any questions on the theory part so far? No? Because now we're just going to go back and do some examples and then get you to sort of feel how it feels like. So that's 15A, 15B. Cool? All right. Here we go. So that was the theory. Let's go to now doing the formulas. Here we go. Didn't I have an example? There we go. Here it says, find the expected value of the random variable x. They don't tell you it's continuous, but what was the key that made you know or tell you that it's continuous random variable? Good. That's how you tell when you're in the exam. If they say it's probability density function, you should already be thinking integration. There is no binomial and there is no discrete in that case there. It is continuous. So you're already in your head, you should be thinking of the integration of x times f of x is your e of x, or your variance of x is e of x squared minus e of x all squared. That's what you should be thinking about when you're doing these kind of problems. Okay? Now, because I know it's a probability density function, you can either try to picture this graph here, but because it says 0 from less than 0 and greater than 2, then I already know from 0 to 2, I've got a graph. Everywhere else is 0. Everywhere else is 0. I just need to know what 0.5x looks like. 0.5x is a linear line. So I can draw it however I want. I can just go like that. There we go. That's my graph. It's a straight line. I just need to know the endpoints. Whoops. I need to know the endpoints. This is obviously 0 if I sub x equals 0. But if I sub x equals 2, what should this coordinate be? 1. So when it's 2, it's 1. So now, I know the height's 1. I know the distance is 2. I can actually find the area. Now let's check if this actually is a probability density function, because apparently the area has to all sum up to 1. True? Now, from the left and from the right, that's 0 already. So the only thing you have to work out is the triangle that you have. The triangle. Area of a triangle, which is half base times height. Base is 2, half the base is 1. 1 times 1 is 1. This is a probability density function. So you don't have to check it. It's just that if you get in an exam question and they ask you to find A or whatever it is, you now know how to do it. Because you know as soon as they say probability density function, the area has to equal to 1. Integrate it. it has to equal to 1, or area of it has to equal to 1. Okay? Now, the question isn't asking for me to prove its probability density function. The question is asking me to find the expected value. How do I find the expected value again? What's the formula? What do I do? What do I do? How do I find expected value? What did we just say? Yeah. It was x times your f of x, integrate that. Because when you integrate it, you find the probability. So, if this is your formula, e of x is x multiplied to the function. What's my function? Well, from here, I can already say negative infinity to infinity, it's x multiplied to, what's f of x? It is 0.5x, but it's 0.5x not from negative infinity to infinity, it is 0.5x from where to where? 0 to 2. Everywhere else is 0. You don't need to write that down. So you need to fix this equation to integrating from 0 to 2, x times 0.5x dx, which really, if you simplify that, that's just 0 to 2 of 0.5x squared, which we should know how to do that. That's chapter 11, integration. So if I were to do that now, I can just take out the 0.5, which is half, integrate just 0 and 2, x squared dx. I should know how to integrate x squared, and we know integration of x squared, which is x cubed on 3. Okay, add the power by 1 and divide it by the n plus 1. Yeah? So in this case here, I've got half multiplied to x cubed on 3, sub in 0, sub in 2, and you can find out your area. Okay, if you sub in 2, 2 cubed is 8, so 8 on 3, minus if you sub 0 in, well, it's going to cancel out to be 0. So really, you've got half multiplied to 8 on 3, which works out to be 4 on 3. Now, before we move on, I want you to think, what's 4 and 3 represent again? What does it mean when I got 4 and 3? So it's not about just getting the answer, it's about interpreting it. What's 4 and 3 mean? Yes, Nas? Yeah, but what is expected value? What is the expected value? We did this in chapter 13. What is the meaning when you have the expected value? What does expected value mean again? What is the expected value? The mean. It's the average. So they're just saying, on average, between 0 and 2, your average is 1 1/3, 4 and 3. 1 1/3 is my average between 0 and 2. It's not the middle. The middle is the 50th percent. The middle would be 1. My average, in this case, 1 1/3. Okay, and that's key because when you're doing applications or extended response questions, you need to know what the 4 and 3 means. Because if they're talking about cars, number of cars that return, you've got about 1 1/3 cars that return. That's the expected. So then how you answer your question based on you can't have 1 1/3 cars. You either get a bit more, so you either get 1 car only, but that's below the expected. So how many times or how many cars will come? About 2. 1 1/3 will, instead of 10 to 2. 2 cars is what I expect. So that's how you answer the question. But you see, the difference is if the question was like, what number of how would they word the question? They'll say something like, find the number of expected cars that would return from Melbourne to Sydney. So that could be an extended response question. And you just need to understand that you have to find expected value, and expected value means done. It's interpretation. So you learn a technique, application, extended response, apply it. Okay. So how do we feel with that? Did that kind of make sense, what we're doing there? Just the how-to? Okay, so I taught you the theoretical. This is now the how-to. And it's the same thing for variance. So if you were to do the variance, exercise 15B, so if I go down to an example for variance, let's try this one. I'm going to delete all these. Same idea, same theory, same graph again. We're already found, and what did I do? Oh, sorry, I'm giving you part of the answer. Okay, I want you to find the variance now. So you now know the expected value, which I'll write down again. We had the expected value as 4 on 3. That was our answer. I want you to use that now to answer how to find the variance of the exact same graph. Okay, same continuous problem. And you'll see how easy it is to do 15B, 15C will be the same thing. The hardest part is understanding the theory. Get the theory, understand how to apply it. This is just the how-tos. Okay? We'll be on to chapter 16 before you know it. And then before you know it, we're done. Or at least I'm done with you. Yeah. Done with you. Let's go. Find the variance and standard deviation. Just to recap, how do you find standard deviation again? How do you find standard deviation again? Square root of variance. Can someone explain to me why do we square root variance again? What is standard deviation describing? How off you are. It's the error. It's more of the accurate error, so the plus minus errors. On average, what's my error? Okay. So I have a prediction. Standard deviation tells me the rough error. Okay. Hands up if you got variances 2 over 9. Very good. And then standard deviation is just square root of that. Okay. So I use the computational formula. I found E of x squared first. E of x squared just finds the mean, but the x variable is an x squared, so I do x squared times the function. X squared times 0.5x between 0 and 2, because everywhere else is 0. Comes x cubed, I took out the half. Integrate x cubed, I get a quarter equal to 4. Sub in 2, sub in 0, I skipped a couple of steps, I know sub in 0 just cancels out. Sub in 2, 2 to the power 4 is 16, 16 on 4 is 4, 4 take away 0, times the half, 52. So I now know E of x squared is 2. So now I'll do 2 minus E of expected, which is what we calculated before, squared. 2 minus 16 on 9. 9 times 2 is 18. 18 minus 16 is 2. But there you go. That's exercise 15B. You're falling behind. But like I said, everything goes back to chapter 13. So if you learn chapter 13, 13C, 13D, it's the day that I ran up and down, where it came from EBIS, that was the sort of nut and bolts of everything, expected variance to understand. Yeah? But it all applies to every single chapter until you finish this course. But So every other skill you've learned already, you've learned enough algebra, you've learned enough from calculus, enough functions. There is no more functions to learn. It's only now understanding the theory for probability and applying. There you go. I'm going to see if I had put some exam questions or not. No exam questions. There you go. Oh, actually, one last thing in case you didn't listen yesterday. And this might be a good part of information. The median means the 50th percentile, which means that whatever the graph is, it's when you have probability of getting it is 0.5, 50%. Okay? So when we say 50th percent, it's negative infinity to m, because wherever m is, that should be half the chance. Okay? So hence equals to 50%, but 1. Negative infinity to infinity is 1. Negative infinity up until this m value. If it equals 0.5, we call that the median. So there you go. That's it. That's your mean. I have a feeling that variance was 15C. I have a feeling. It's not the summary. So maybe I already showed you C. That's 15B, 15C. Hardest one is 15A. Get the theory, get the logic, understand it, then apply. Everything else is the same. There you go. Done for today.